Okay, so 4.3 basic trigonometric identities. Students will be able to use various trigonometric identities to simplify, evaluate, and solve given trigonometric problems by completing problems as taught. Okay, so we're going to talk about some trigonometric identities, and we're going to take this lesson very slowly. Okay, so today you're going to be introduced to the basic trigonometric identity. We'll do some examples, and then we'll come up here. Oops, sorry. We'll come up here and we'll do the challenge where you simplify, okay, your trig expressions. And then we're going to stop here for today, and we're going to work on our classwork, okay? Next time that we meet up, we're going to tackle even and odd trig identities, okay? And then we'll practice that. And then the next time, so this is going to take like a good 3 different lessons for us, okay? And then we're going to do supplementary and complementary identities with trig. Okay? And that's pretty much the end of our trigonometric identities. But it's going to take us some time because last year I taught it all at once and then we practiced, and kids really had trouble differentiating them. So we're going to take it slow and steady this time around, okay? Okay, so let's go ahead and get started on our first part, okay? Our first part here. So I have our trigonometric functions review, okay? So remember that we have our trigonometric functions review. We have our SOHCAHTOA. You guys remember that? Okay, so I wrote it last time. I wrote it in a little bit different of a way. I wrote S instead of OH real big. I wrote O over H. So, right? So sine is opposite over hypotenuse. Ka, adjacent over hypotenuse. And TOA, tangent, opposite over adjacent, right? So this is our basic form from our right triangle trigonometry, right? So suppose we had our theta here. We have our opposite side here. We have our adjacent side here, and we have our hypotenuse right there. Okay, that's our basic right triangle trigonometry, okay? But then when we talk about trig in terms of the unit circle, okay, when we talk about it in terms of the unit circle, this O and H, the O and the A changes to our X and our Y. So in the case of our unit circle here, right, our cosine is equal to our X here, and our sine is equal to our Y here. And so sine of theta is equal to Y over 1, which is just Y. Cosine theta is equal to X over 1, which is just X, right? 1 is our hypotenuse. Excuse me. And tangent theta is equal to Y over X, opposite over adjacent, right? Or you can look at this as, since sine of theta is equal to Y and cosine of theta is equal to X, you can look at it as tangent of theta is equal to sine theta over cosine theta, okay? This will become very important as we work through identities, okay? So you want to notate these guys and remember those relationships there, okay? I'm looking for my highlighter so I can highlight this. There we go. So we have our sine theta, we have our cosine theta, and we have our tangent theta there, okay? Now, because of this, we come to our basic trig identity here, okay? Actually, before I do that, I want to talk to you guys about our quadrants here, okay? I want to talk to you guys about our quadrants here. So since our x and our y, right, are the cosine and the sine, we can identify the signs of each of them in each quadrant. So for example, right, this is quadrant 1, 2, right? This is way back in like pre-algebra, 3, and then 4. So it goes counterclockwise there, okay? And I want us to take a look and see, right, in our quadrants, I want us to notate which function is positive and negative in each quadrant. So in quadrant 1, right, if we take a look in quadrant 1 here, we can see that both our x and our y are going to be positive here, okay? So over here in quadrant 1, we're going to have positive comma positive for our coordinates, okay? So everything, any function, whether it's sine, cosine, or tangent, okay, is going to be positive here, okay? In quadrant 2, our y ends up being positive because we're still in the positive. Our x, however, is now negative, okay? So that means our cosine will be negative here, and our sine will be positive here, okay? Our cosine will be negative, and our sine will be positive, okay? So then we come into quadrant 3, and in quadrant 3, we're now in negative for the y as well. So we have a negative and a negative. So we have negative and negative here, okay? And then over here, we come down to quadrant 4. In quadrant 4, we are now back in the positive for x, and we're stuck in the negative for our y, okay? So all of our functions, including tangent, because tangent is sine over cosine, right? So if they're both positive, that means tangent will also be positive here. So all of our functions are positive when they're in quadrant 1. So what does that mean? That means if our angle is in quadrant 1, then our values are going to end up being positive, okay? In quadrant 2, our cosine is negative, but our sine is positive, okay? Our sine is positive here. In quadrant 3, both cosine and sine are negative. What happens when we do negative over negative, though? Negative divided by negative gives us positive, which means our tangent is positive here, okay? And then when we come over to quadrant 4, our cosine is positive, our sine is negative, so our cosine is positive here. There's a little saying that helps you remember what's positive in each quadrant, okay? And it starts with all. Over here for the S, we have students. For the T, take. And for the C, calculus. So all students take calculus. All functions are positive. Sine is positive. Tangent is positive. Cosine is positive. All students take calculus. Okay. So the reason why I bring this up is because this is going to help us a lot when we start dealing with different thetas, and determining what quadrant our theta is in will allow us to automatically know what the signs of our values are going to be, whether they're going to be positives, positive, negative for one, both of them are negatives, or positive, negative for one again. Okay. All right, let's take a look now. So our first trig identity is the identity of sine squared theta plus cosine squared theta is equal to 1. Okay, this is our first identity. This is a very important identity, okay, because a lot of other things can stem from this identity. So for example, if I were to subtract over my cosine, I could get sine squared theta by itself, and I would have 1 minus cosine squared theta. Okay, I can similarly do the same and subtract over sine squared theta instead. And I would get that cosine squared theta is equal to 1 minus sine squared theta. Okay. Now this identity stems from the Pythagorean theorem. This identity stems from the Pythagorean theorem using our triangle here. So we can use the Pythagorean theorem, okay, on the right triangle formed with the unit circle. So if you remember, our Pythagorean theorem is a squared plus b squared equals c squared. Excuse me. Okay, our a, right, these are our legs, a and b. So that's going to be x and y. Okay, that's going to be our x squared and our y squared. I'm sorry. Yeah. So if we bring in our x, we'll have x squared plus our other leg, y squared, is equal to our radius in the unit circle. Sorry, our radius in the unit circle is 1. So it's going to be 1 squared. Okay, well, we know that x is equal to cosine theta, right? So I can simplify, I can separate this and I can say, well, x squared is the same thing as cosine squared theta plus y squared. Okay, that's sine, so sine squared theta is equal to 1. And that gives us our identity. So this identity stems directly from the unit circle and the Pythagorean theorem. Okay. All right. So we can use this identity to essentially simplify other expressions, trig expressions, help us to write them in more simpler terms. Okay. But before we put this identity to use, we want to use some right triangle trigonometry, okay, to find the value of the trigonometric functions that based on the given information down here. Okay. So let me move this over so I can put this up. Okay, so this is what we're gonna do. We're given one of our identities, okay? And this is where we're going to be using our SOHCAHTOA, okay? So once again, let's bring that down here. SOHCAHTOA, okay? So we're given that sine theta is equal to 8 over 17. We want to find cosine theta, okay? We want to find cosine theta. So 8 over 17, that's not really a value that we can find on the unit circle. So what we do is we go ahead and we create a right triangle. Now, since this is positive, right? Since this is positive and this is positive. We're going to put this in quadrant 1. Okay, we have a right triangle. Here's our theta. Now, sine is opposite over hypotenuse, right? Sine is opposite over hypotenuse. That means this sine theta is equal to 8 over 17. This is our opposite. This is our hypotenuse. So I can label my triangle here. My hypotenuse is right over here. That's 17. And my opposite side is 8. Okay. Now I want cosine of theta, which means I need my adjacent side. I need that guy right there. Okay. Cosine is adjacent over hypotenuse. So I know this is going to be over 17, but I need to know what my adjacent side's value is. And so we use something that we've known for years, which is our Pythagorean theorem. Okay. Remember that your hypotenuse will always be C, right? So we have 8 squared plus, we can call it A squared is equal to 17 squared. And we're going to go ahead and we're going to solve that. That's going to be 64 plus A squared is equal to 17 squared, which is 289. Okay. And then subtract over the 64, we'll get that A squared is equal to 225. And then we're going to square root both sides, and we will get that A is equal to 15. The square root of 225 is 15, right? The calculator will tell you that much. So we get our adjacent side as 15 right over here. So cosine of theta, of the same theta, is going to be 15 over 17. Okay, simple, straightforward. If we wanted to, we could also find tangent of theta here, right? Opposite over adjacent. So 8 over 15. But they only asked us for cosine. They only asked us for cosine. Okay. Now, sometimes we're given a negative value. Okay, and it's not, we're not given one here, but I'm just saying sometimes we're given a negative value. The negative always applies to the opposite or the adjacent. Okay, your hypotenuse, and make this little note for yourself. Okay, your hypotenuse, okay, is always positive. So your negative will always apply to your opposite or adjacent value. Okay, it does not, it never applies to the hypotenuse. Okay, that's just a side note there. Excuse me. So let's see here. We have cosine of theta, right, is equal to 3 over 5. You want to find sine of theta. So sine of theta. Okay. Cosine of theta is 3 over 5. That 3 over 5, it's cosine, so that's going to be adjacent over hypotenuse. Okay, so that's adjacent and that's hypotenuse. Okay. Both of these are positive once again, so we can go ahead. We have no indication of our angle being in any other quadrant here, so we're going to go ahead and draw a right triangle here. Again, our theta is always at the angle with the vertex at the origin. All right, we're never going to put theta up here in this right triangle. So it's going to be over here. Okay. All right, so adjacent over hypotenuse, my hypotenuse is 5, so that's going to go there. Okay, my adjacent side is the one touching theta, so that's going to be 3 right there. For sine, I definitely need my opposite side. Okay, so I'm going to do the same thing. I'm going to use the Pythagorean theorem and solve. Okay, so I have 3 squared plus, I don't want to use O, so I'm just going to use x. 3 squared plus x squared is equal to 5 squared. Okay, that's going to be 9 plus x squared is equal to 25. X squared equals 16. right? Square root both sides, we're going to get x is equal to 4. So we have 4 here for our opposite. So our sine theta will equal opposite over hypotenuse, which is 4 over 5. Okay. Why don't you guys go ahead and try this one? Okay, sine theta is equal to 7 over 25. Okay, you're being asked for tangent of theta. Okay, tangent of theta. It does not change how you solve anything. Okay, it's just the final ratio is going to be opposite over adjacent. Okay, so I'm going to give you guys a total of 5 minutes. If you finish before the 5 minutes, privately message me the ratio for tangent of theta. Okay, private message me the ratio for tangent of theta. I'm going to give you guys 5 minutes to solve that one on your own. Okay, so what did we do here, guys? The whole purpose for these two using our basic trig identity of sine squared theta plus cosine squared theta equals 1, right? We were given two quantities, right? We were given two quantities that were being multiplied together. Individually, it's just cosine and cosine. This is dealing in the squares. So I multiply them back together. Pretty much like a reverse difference of squares here. Multiply them back together and got 1 minus cosine squared theta. Well, 1 minus cosine squared theta is equivalent to sine squared theta. So I can rewrite that as sine squared theta. Okay. Over here, we had sine squared theta and a tangent squared theta. When you have a situation like that, you always want to rewrite tangent. Okay, you want to rewrite tangent and put it in terms of sine and cosine, because tangent is equal to sine over cosine. Okay, so similarly, tangent equals sine over cosine, then tangent squared equals sine squared over cosine squared. So we can we can replace or substitute this tangent squared theta with sine squared theta over cosine squared theta, which then allowed us to take this fraction, skip, change, flip it, and then notice our sine squared theta is canceled out, and we were left with just cosine squared theta here. So 1 minus cosine squared theta, which again is equivalent to sine squared theta. And so that simplifies down to just sine squared theta. This is essentially the gist of using your basic trig identities, okay? So in your 4.3a, okay, in this 4.3a, you are you're using the right triangle method that we were using in the front here, okay, to solve for your missing values or whichever one they're asking you for. Okay, remember that SOHCAHTOA Sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. Tangent equals opposite over adjacent. That's going to be your BFF for 4.3a. Okay. So 4.3a, you're doing the right triangle method. Okay. And there's only 8 questions there. 4.3b, okay, you only have the 5 questions on the front page. Okay, you are simplifying your expressions here. You are simplifying the expressions here. Okay. All right. So you have a solid 30 minutes to work on your classwork. Okay. If anyone wants to be put into breakout rooms with a friend to get their work done, let me know. Okay. If not, I am here and you are more than welcome to ask me questions. Okay. Okay, so we want to find cosine of theta, and we're given that tangent theta is equal to negative 1 over 5. Okay. So remembering that tangent is adjacent over hypotenuse, right? Remembering that tangent is, I'm sorry, not adjacent, opposite over adjacent, right? Tangent is opposite over adjacent. And I said on our notes that the hypotenuse is always positive. That means the opposite or the adjacent side can be negative. So in this situation, which one is it? Is it the opposite or the adjacent side that's negative? Well, that's what this sine theta tells me. Okay. If they tell you that sine theta is greater than 0, then they're telling you that sine is positive. Okay. So our sine here, right? Remembering that tangent theta is also sine over cosine. Okay. And if they're telling you that sine is positive, they're essentially telling you that this negative is on the cosine. Okay, that's what that tells you. Because they're telling you that sine is positive, they're telling you this negative applies to the cosine there. So when we draw our triangle here, that means our sine is positive and our cosine is negative. Well, the quadrant where sine is positive but cosine is negative is quadrant 2. So when we draw our triangle here, we're going to be drawing it in quadrant 2. Okay. And so we'll have our theta again at the origin, right? At the angle that's at the origin. And we know that our cosine here, our x is -5. Our sine, our y is 1. I know my triangle is definitely not to scale. Ignore that. Okay. So this allows you to know that the cosine is where the negative goes. So when you go ahead and you find your hypotenuse, because they're asking you for cosine theta, right? Cosine theta is adjacent over hypotenuse. So when you do your Pythagorean theorem here, you'll have -5 squared, right? Make sure that's in parentheses, plus 1 squared is equal to our, we're going to call it h squared. You can call it x, you can call it any letter you want, okay? -5 squared, that's going to be a positive 25 because -5 times -5 plus 1 is equal to h squared. Okay. So this is 26 is equal to h squared. And if I square root 26, it's not going to be a perfect square. It's going to be 5 point something something, or you can just leave it as the square root of 26. Okay, so our hypotenuse is equal to the square root of 26. We want to keep it accurate. Okay. You can try to also simplify that, but that's just 2 times 13, and then you can't go any further than that. I hope some of you guys caught that. Okay. So there's no perfect squares in 26. So then when I want to do cosine theta, okay, it's going to be adjacent over hypotenuse. My adjacent is -5, and that's why it's so important that you know where the negative goes here. okay? Because now my cosine is going to be negative 5 over the square root of 26. You can leave your answer like this, but we just keep in mind that eventually we are going to be rationalizing this, where we would do negative 5 times the square root of 26. And then to get that radical out of the denominator, we multiply top and bottom by the same radical. And we'll get negative 5 square root of 26 over 26. So that would be the real answer here. But for right now, I'm okay with this. I'm okay with the negative 5 over the square root of 26. Okay, but the whole point of this is, why are they giving us that sine theta is positive, is greater than 0? Okay, they're telling you that to let you know that the sine, the opposite value, is positive. That means the negative applies to the cosine value here. Okay, so when they give you this, they're helping you figure out the quadrant. They're helping you figure out that quadrant. Okay, so over here, they give you that cosine theta is 3 out of 5, positive, right? So that's positive. And they're telling you that sine theta is greater than 0, which is also positive. So which quadrant is both cosine and sine positive in? Yeah, quadrant. Yes, Wally. Thank you. Yes, Oswaldo said quadrant 1. Yeah. Okay, so the quadrant that both sine and cosine are positive in is quadrant 1. So this tells us that tangent will also be positive, because if sine and cosine are both positive, then tangent is also positive. So when I draw my triangle, I'm going to be drawing it in quadrant 1. Okay, so this is Q1. This was quadrant 2. Okay, all right. I'm going to let you guys continue working.